presenter, Victor Petrenko here, Victor Karachenko, no, Georgy Levchenko, only one, Bogdan Mordyuk, very interesting. I think that we have 3 minutes else. We have first presenter and second. Very good. Let me begin our session. Slava Ukraini! I hope that our presentation will be very useful, fruitful, and simply nice, interest for all people who are living inside our auditorium. The first presentation, instead Andrei Horyachko will be presented Dr. Vladimir Dubinko from Kharkiv Institute of Physical and Technology. Your presentation titled Heterogeneous catalysis driven by localized anharmonic vibration at nanoclusters. Please.
Good afternoon, ladies and gentlemen.
15 minutes.
I repeat the title of my presentation, which is Heterogeneous catalysis driven by localized anharmonic vibrations at nanoclusters. What it's all about is actually, every one of you know that there is no general theory of catalysis. There's a lot of models, and usually these models are based on ad hoc structural features of catalysts. And here I would like to present to your attention kind of a general approach, which is not supposed to explain every catalytic reaction, of course, but maybe some part of it, which is based on not on just a structural feature, but on a nonlinear dynamic of atoms which composes the reaction site. So the content is as follows. We shortly review Arrhenius law and the Kramer's escape rate, which is behind this law, and then we consider these localized anharmonic vibrations of atoms, which will be viewed as the mechanism behind some of the catalytic reactions. And then we consider modification of the reaction rates, taking into account of these localized anharmonic vibrations, both at high temperatures, where the thermal fluctuations dominate the process, and at low temperatures, where the quantum tunneling is significant. So, Arrhenius law is very well known, and it explains that the chemical reaction usually obeys the exponential law with the dependence of on the activation barrier, which is here, if I can point it now. Yeah, it's yes. This one, yeah? This one. Yes, thank you. So this is activation barrier, yeah? And if you know this barrier, activation energy and temperature, you are supposed to know everything about the rate of reaction, and it has been formalized by Kramer's in 1940, actually who considered this problem of escape from one potential well to another via the barrier, and actually derived this formula, which practically explains the physics behind the Arrhenius law. But what if at the reaction site we have large amplitude vibrations of atoms? Okay, for instance, like here. There's an example showing you the iron. This is a 3D structure, and we just shifted a few atoms from the equilibrium positions, and then the computer MD simulation has been started, and it is 0K. But you see that these 3 or 4 atoms are performing these time periodic vibrations, and it will last several hundred of oscillation cycles. So it's something different from the phonons. The phonons are delocalized, and here we have a localized anharmonic vibrations, and the reason behind the stability is that the frequency of these vibrations goes beyond or above or below the phonon frequency. That's why it's so persistent. If we take into account these phenomena in the reaction model, we will see that it can explain the time periodic driving of the potential landscape itself. And when you calculate the result, you will see, as we did probably 6 years ago, it's a published work already, that when we drive the potential barrier, the result is that the reaction rate, which is escape rate, is multiplied by amplification factor. And amplification factor depends on the driving amplitude, V, and on the temperature in this case. And we see that, for instance, for amplitude like half of EV, we have the amplification factor of the order of 10 to 10. So 10 orders of magnitude, the reaction can be faster, in spite of the fact that the driving of the barrier is symmetric. But when the barrier becomes shallower, it gives a huge acceleration to the reaction. And there are some analyzed reactions using this model, for instance, like transformations in this mica crystal. There is some transformation which usually takes takes a few days at high temperature, like 600, say. But the estimation by Arrhenius law would predict at room temperature at 300 C would predict 1,000 years. But experiment shows that it can go in 3 days as well, and there's indication of this behavior in this particular case, and some mathematical analysis show that indeed we can accelerate this reaction by 4 to 5 orders of magnitude with this mechanism. The big question is how to extend this concept to include quantum effects, that is tunneling. In this case, instead of temperature, we can consider some function which actually composes both effects due to thermal fluctuation and due to quantum noise. Then the question is, can we increase the quantum noise? Because when we can increase thermal noise just by heating, how to increase the quantum noise? Usually we know that the harmonic oscillator is a very well-known thing, and we know that the energy levels are more or less fixed, and it depends just on the curvature of the barrier. But if the barrier is breathing like that, the situation drastically changes. And this change is Vladimir. Yes. And then situation changes in that case that somehow again. I'm not sure that the battery is okay.
Don't worry.
Good. From the beginning. And we will see that in this case, the wave function, which is from the beginning, at the stationary state, is concentrated at the bottom of the well. Well, you drive the well, it becomes broader and broader, and the energy of the zero state increases exponentially with these driving cycles. And when you calculate the result, we will see that with the number of driving periods, the escape rate start increasing very, very fast, also many orders of magnitudes. That's why, for instance, when it's possible to solve the Schrödinger equation for a double well potential and compare the results for the stationary landscape and this periodically driving landscape, and you'll see that in the first case nothing happens, so reaction doesn't occur. Tunneling is not visible because the distribution function is the same after 10, 50 or 100 cycles. In another case, we see drastic changes, and after 100 cycles, already the probability to find the particle in either of the wells is more or less equal. That's why we are looking for medium for which can support appearance of these localized anharmonic vibrations, and the guide is that small activation gap is required for LAV formation, and this is possible for nanoclusters. This is one of the examples. It's a molecular dynamic simulation of nickel nanoparticles, 2,000 of atoms, and the median temperature is 100 K, but the color shows you what can be called the local temperature. It's not a temperature actually, because it belongs to one atom. It's Debye-Waller factor. It's an amplitude of vibrations of atoms, and it's very broad, and at some places it becomes 10 times higher than in other places. So these can be viewed as a catalytic centers, you know. That's why the small size is important, and we all know that real nanoparticles can be much stronger catalysts than is expected just from the surface effect, let's say. Also, for instance, here is another example of palladium nanoclusters consisting of some magic number of atoms which make the stable closed structure, and the result is that it can be, if you shift it a little bit, it starts, you know, vibrating in very coherent manner. That's, to my mind, is the first illustration of real 3D discrete breather, as we call it, which is discrete because it has a crystalline structure, and a breather, it like breezes, you know. And so, in summary, my goal was to tell you that we present in reaction rate theory, mostly in solids, yes, which is modified, taking into account the localized and harmonic vibrations, yeah, that can appear in nanoclusters, resulting in strong catalytic effects. Yes, account of these effects at low temperatures with the count of 0-point oscillations shows that LIV can be strong catalyst not only at high temperatures, but also at low temperatures. And further investigations in this field, based on atomistic model of LAV, may open new ways of engineering catalysis, as we hope. Thank you for your attention.
Thank you very much for your amazing presentation. Question, please. But for me, please question. You say about all the magic cluster only 55 items. What this prison effect will be assured if size of cluster will be 100? No, the next magic cluster. It only depends from size.
Yeah, thank you. This is a good question. If you have a look at this slide, you know, this is a formula which calculate the magic numbers. Yes, it's 13, 55, 147, then 300, etc. Now we are trying to model all of these, you know. Well, for instance, the problem with the smallest, 13, is it's very unstable. It's just, when you just touch it, it disintegrates. This 55 shows the spectacular behavior. And we didn't, we are just starting playing with 147, etc. So it looks like the bigger is cluster, the more stable it is. And so the question is whether we will be able to organize this type of behavior in the bigger ones. But currently we are thinking about this 55 and 147 as the candidates. That's why we are trying to produce experimentally, to look for guys who can produce experimentally just 1 nanometer size clusters, because we expect strong catalytic effects precisely in this region.
Yes, of course. Maybe this situation, the prison effect will be when one magic cluster constructed in next magic cluster with free energy. Many free energy, the effect may be, yes.
There's two problems. One, it's very, as you probably know better than me, it's very difficult to remain them in this state, not to coagulate, etc. That's why we can fit it somewhere. And the other question is the influence of support. Yeah, how it will behave, not in vacuum as we did it, but in some real surrounding.
Yes.
Okay?
No, it's very easy. Comments, question, no? Thank you very much.
Thank you.
Once again.